Howdy, folks. This is Keith Wiggins. So, with PAG Waste Management, we're continuing our talk on Handbook of Biomass Downdraft Gasifier Engine Systems. Sorry for the delay on Chapter 4, but I've been a little under the weather this week, and so hopefully we can get through the rest of this chapter, and my voice won't go on us. We're leaving off at 4.4 Principles of Operation of Direct Gasifiers. So let's look at the intro here. Since volatile organic molecules make up approximately 80% of the products from biomass pyrolysis, the principal task in biomass, but not coal gasification, is to convert this condensable volatile matter to permanent gases. A secondary task is to convert the resulting charcoal also to gas. The most important types of fixed bed gasifiers for this task are the updraft and downdraft gasifiers. These gasifiers will be discussed in greater detail in Chapter 5, but a brief introduction here will facilitate understanding of the fundamental principles involved. The term updraft and downdraft gasifier may seem like trivial mechanical descriptions of gas flow patterns. In practice, however, updraft biomass gasifiers can tolerate high moisture feeds and thus have some advantages for producing gas for combustion and burner. However, updraft gasifiers produce 5 to 20% volatile tar oils and are also unsuitable for operation of engines. Downdraft gasifiers produce typically less than 1% tar oils and are also used widely for engine operation. The reasons for this difference are given below. That's very interesting. So, operation of the updraft gasifier. The updraft gasifier is shown schematically in Figure 4.5a up here. Biomass enters through an air seal at the top and travels downward into a rising stream of hot gas. In the pyrolysis section, the hot gas pyrolyzes the biomass to tar oil, charcoal, and some gases. In the reduction zone, the charcoal thus formed reacts with rising CO2 and H2O to make carbon monoxide and hydrogen. Finally, below the reduction zone, incoming air burns the charcoal to produce carbon dioxide and heat. Note that the combustion to carbon dioxide is exothermic, and the heat produced in the gas here is absorbed in the endothermic reduction and pyrolysis reactions above. And you can see that from here. Depending upon the pyrolysis conditions in a gasifier, one can generate a wide range of vapors, wood oil and wood tar, in the hot gas. If the pyrolysis products are to be burned immediately for heat in a boiler or for drying, close coupled operation, then the presence of condensable vapors in the gas is of little importance. In fact, the condensable tars represent a high energy fuel and greatly enhance the energy obtained from each unit volume of biomass. If the volatile materials are condensed, they produce tars and oils known commonly as creosote. These materials collect in the chimney of airtight wood stoves, the pipeline of gasifiers, and the valves of engines. Most of the companies advertising and selling updraft gasifiers no longer produce them. If the gas is to be conveyed over a long distance in a pipeline, burned in any form of engines, or used as a chemical feedstock, the condensing tars will plug pipes, and sometimes in only a few minutes. In these cases, it is necessary to use a mode of gasification that succeeds in converting the tars to gas. This can be accomplished either by cracking, like a secondary pyrolysis, or by partial oxidation in flaming pyrolysis. Next is operation of the downdraft gasifier. Downdraft gasifiers have been very successful for operating engines because of the low tar content. Most of the work reported in this book was performed on downdraft systems, and there'll be principal gasifier discussed in the balance of this book. In the downdraft gasifier, air contacts the pyrolyzing biomass before it contacts the char and supports a flame similar to the flame that is generated by the match. As in the case of the match, the heat from the burning the volatiles maintains the pyrolysis. When this phenomenon occurs within a gasifier, the limited air supply in the gasifier is rapidly consumed, so the flame gets richer as pyrolysis proceeds. At the end of the pyrolysis zone, the gases consist mostly of about equal parts of carbon dioxide, water, carbon monoxide, and hydrogen. We call this flame in a limited air supply flaming pyrolysis, thus distinguishing it from the open wood flames in unlimited access to air. Flaming pyrolysis produces most of the combustible gases created during downdraft gasification and simultaneously consumes 99% of the tars. It is the principal mechanism for gas generation in downdraft gasifiers. If the formula for biomass oil is taken as approximately CH1.2, 0.5, then partial combustion of these vapors can be represented approximately by the reaction shown below. The exact oxygen to vapor ratio will depend on the exact vapor composition and gasifier conditions. Downdraft gasifiers usually produce vapors that are less than 1% condensable to oil tar, the reason behind the almost exclusive use of downdraft gasifiers as an energy source for operating engines. Although flaming pyrolysis is a new concept explaining biomass gasification, partial oxidation of small and large hydrocarbon molecules to carbon monoxide and hydrogen is a standard industrial process. Texaco has used an oxygen gasifier to oxidize hydrocarbons to carbon monoxide and hydrogen, as in the following reactions for a typical oil. So, formula below. The resulting gas, called synthesis gas, can be used to manufacture methanol, hydrogen, or ammonia. There is some interest in using the Texaco system to gasify biomass, and that's from 1982. Factors controlling stability of gasifier operation. Gasifier operating temperature is a function of the amount of oxygen fed to the gasifier. The temperature response, however, changes abruptly at an equivalence ratio of approximately 0.25. This change point, or Ni, occurs for temperatures of 600 to 800 degrees Celsius, depending on oxygen source. Gasifier pyrolysis produces oils and tars that are stable for periods of 1 second or more at a temperature below 600 degrees Celsius. Since updraft gasifiers operate below an equivalence ratio of 0.25, temperatures less than 600 degrees Celsius, considerable quantities of tars are emitted with the product gas. In the gasifier, above, air is injected at the interface between the incoming biomass and the char. If too much char is produced, the air consumes the excess char rather than biomass. If the char is consumed too fast, more biomass is consumed. Thus, the invert gasifier is self-regulating. Is that right? Invert gasifier is self-regulating. At SERI, we have built the oxygen gasifier, and it's in a figure below. We operate this with a fixed flow of oxygen and add biomass faster or slower to maintain a fixed bed level. In the Buck Rogers gasifier, that's way from my childhood. That's amazing. A fraction of air is introduced through the rotating nozzles and maintains the zone at that level. Some gasifiers operate at lower values of equivalence ratio on purpose by augering charcoal out of the char zone in order to produce charcoal, a valuable byproduct, and to yield the higher gas heating value shown at low equivalence ratios. Such operation is not true gasification, but might be called gas charification. In entrained or fluidized bed operation, the ratio of biomass to oxygen can be varied independently. In this case, the equivalence ratio must be set, typically by fixing oxidant flow and varying fuel flow to maintain a constant temperature. Next, charcoal gasification. We'll discuss that. The manufacture of charcoal for use as a synthetic fuel dates back at least 10,000 years and is closely associated with the development of our civilization. Today, charcoal is used as the prime source for heat for cooking in less developed countries and also is used for the reduction of many ores in the smelting process. The charcoal field from a biomass feedstock is highly dependent on the rate of heating and the size of the biomass particles. Industrial charcoal manufacture uses very slow heating rates to achieve charcoal yields of more than 30% of the initial dry weight of the biomass. The intermediate heating rates used in proximate analysis usually produce charcoal yields of 15 to 20%. The very rapid heating rates encountered when small biomass particles are gasified and combusted realize charcoal yields of less than 15% of the initial dry weight of the biomass. Larger size feedstocks produce 15 to 20% charcoal. During updraft or downdraft gasification, 10 to 20% of the biomass will remain as charcoal after pyrolysis is complete. In an updraft gasifier, air entering at the grate initially burns this char to liberate heat and CO2 according to the reaction shown below. It's carbon plus oxygen, carbon dioxide plus heat. Almost immediately or even simultaneously, the carbon dioxide and any water present in the gasifier react with the char to produce the fuel gases, carbon monoxide and hydrogen, according to the reaction shown below. The first reaction is called the Bordian reaction. This is carbon plus carbon dioxide is two carbon monoxide molecules. So the Baudard reaction. And the second is called the water-gas reaction. So carbon plus water is carbon dioxide and hydrogen. They have been studied extensively for the past 100 years in connection with coal and biomass gasification, since the principal product of coal pyrolysis is coke, or carbon. The rate of reaction has been studied by measuring the rate of disappearance of carbon, coal, or charcoal while passing water or carbon dioxide over the solids. Both of these reactions require heat, and they are endothermic reactions, and therefore cool the gas about 25 degrees centigrade or Celsius for every 1% of carbon dioxide that reacts. These reactions occur very rapidly at temperatures over 900 degrees Celsius, and their cooling effect helps to keep the gas temperature from rising above this temperature. Below 800 degrees Celsius, the reactions become sluggish and very little product forms. We have modeled the reactions of downdraft char gasification using known kinetic values and find that the temperatures measured in char gasification correspond to those observed in the gasifier. We refer to the process observed in an actual bed of char as adiabatic, or no heat input, char gasification. The carbon monoxide, and hydrogen formed in the hot char zone can react below 900 degrees to form methane according to this reaction. So carbon monoxide and 3 hydrogen molecules form methane and water. This reaction proceeds slowly unless there is a catalyst present. However, it is quite exothermic and can supply heat if suitably catalyzed. Concurrent with the emergence of biomass as an important energy source, it was natural that coal gasification interpretations would be carried over to explain biomass gasification. Even today, most articles on biomass gasification use only equivalents and to explain biomass gasification and ignore some other equations. So it's talking about equations, even though what some of these equations apply to 80% of the biomass volatiles. Biomass pyrolysis produces only 10% to 20% of charcoal, and the charcoal is very reactive. Therefore, this cannot be the primary explanation for the conversion of biomass to gas. So in summing this up, in summary, the task of a gasifier is threefold. One, to pyrolyze biomass to produce volatile matter, gas, and carbon. Next, to convert the volatile matter to the permanent gases, carbon monoxide, hydrogen, and methane. And lastly, to convert the carbon to carbon monoxide and hydrogen. These tasks are accomplished by partial oxidation or pyrolysis in various types of gasifiers. So that's our chapter 4. Next, we'll go into the actual gasifier designs. That should be pretty interesting. And I will talk to you next time. Thank you.